Good afternoon, students. Today we are going to cover advanced topics in SQL. Particularly, we are going to look at the spatiotemporal queries that we can execute on a database management system. The outline of this class will be as follows. First, we talk about different types of projections that exist to view our planet. Next, we talk about different types of geometric objects. Later, we look at creating tables to store these geometric objects. Finally, we look at the SQL queries to perform on geometric objects. So, a projection actually means how we see our earth on a piece of paper. That is called projection. So, the concept of projection was first came from the European countries in the field of cartography. So, in cartography, a map projection is a way to flatten a globe surface into a plane in order to make a map. So, actually, this problem occurred because around 13th century and 14th century, the Europeans want to map the entire world so that they can create sea routes to various countries. This requirement raised to create the world maps. So when the concept of world maps came into the existence, people thought of how to view a three-dimensional sphere of earth on a piece of paper. To solve that problem, the concept of projections came here. So you can see here, this is the oldest atlas or the world map that was created by the researchers. You can see here, this part represents the Europe. This is Africa. Okay, this is Saudi Arabia, Iran, and so on. This is India. So this is the map of the world that was known to us. If you observe, there was no American continents here because people were unfamiliar with America. That is the reason that was not there. So let us see different types of projections. The basic one is called cylindrical projection. So in the cylindrical projection, what we try to do is assume that the earth is made up of a glass. Okay. So once we assume that the earth is made up of a glass, inside the glass of earth, put a light source and glow it. And then around the glass of earth, put the paper. Okay, this form is called cylindrical projection because we are covering the earth with the paper. Once we cover this earth and take it out, the light will come inside and falls on the paper. That generation is called cylindrical projection. So the advantage of this cylindrical projection is very simple. Since the area at the equator is touching to the cylinder, the areas at the equator are represented correctly. However, areas at the ends, okay, like Antarctica, Greenland, and all, they will get distorted because the light that is coming from near the poles will get diffracted. That is why the places that are at the North Pole and South Pole look very long. For instance, if you see Antarctica on the world map, you will see that it is covering all the way from Asia to America and it looks very big. But in fact, Antarctica is a very small continent. The biggest continent in the world is Australia. So imagine that Antarctica is smaller than Australia continent. Okay, both are islands, but you can see Antarctica looks much bigger than Australia. So this is the drawback. The places at the poles, even the Greenland, it looks so big, but they are very tiny countries. This is the problem. So how do we solve this problem? Very simple. Instead of putting the cylinder to the edges, okay, put the cylinder so that it touches the poles. Now, if we do this kind of a cylindrical projection, the places that are at the poles, like Antarctica and America continents, okay, European areas, they look correct. But places at the equator will get distorted. You can see here the Africa got very big. So this is the problem. So each country, depending upon its location, it chooses its cylindrical projection in the olden days. The key question is, this cylindrical projection is good for poles or for the equatorial areas. But if you want to draw the map of areas that are like here, like Europe and so on, both of these cylindrical projections may not be good. To solve that problem, people have come up with the projection called conic projection. In the conic projection, what people will do is, given the earth, you can take a paper, make it into a cone and put it over the earth and send the light. This will create the conic projection. If you observe the conic projection, the places that are close to the poles, they look at the exact area because this is the area that is touching the earth. That's why they look in the correct way. And the disadvantages, places away from the poles will get distorted. That is the problem. So each country, depending upon the location in the map, they follow different types of projection system. Since India and Japan are not situated very close to the poles, we generally follow cylindrical projection. If you go to higher altitudes like Europe, okay, Sweden, Norway, they generally use conic projection. So this was the projection type in the olden days. Around 19th century, okay, people started arguing that Earth is not a sphere. It is more looks like a spheroid. So we should not use cylindrical or conical projections to capture that. This was the argument made by the researchers in the 19th and 20th century. To solve this problem, they came up with this oblate ellipsoid shape. Okay, so actually the earth looks like this. Okay, so this is the shape of the earth. So we have central meridian here and the equator. So this way they try to map it. And finally, the research on projections, okay, around 2000 AD, saturated, and they came up with the standard projection system for the entire world called web marketer projection. So this one is also called WGS. Okay, so this is the standard, and this projection contained how to map the entire earth in a very effective manner, which is based on the spheroid shape of the earth. In 2005, Google adopted this projection system in its Google Maps. Since then, this became the universally accepted projection system. So if you see any maps, Google Maps, OpenStreetMaps, so on, they all are using this standard, okay, WGS 84. This is popularly called EPSG 3857. So this is the major one. So every year, small research extensions were done, and finally, we are currently at this projection system. Okay, we are using web marketer projection system, which version is 4326. So this is the version that we are using. So whenever you are opening the Google Map, please keep in mind that we are using web marketer projection system whose number is 4326. So this is becoming very popular and we use this one commonly. So here is the information on the web marketer projection used in the Google. If you want to see more information, please check this link where you will learn different types of map projections that the cartographic researchers have exploited to map the earth. Okay. So now we have understood how we try to map the earth. Now, the key question that comes in mind is how do we represent the map? Okay. So, to represent the map, we have two formats. The first format is called raster format. Raster format is nothing but a photograph, like a JPEG file. So, whenever we take a photo, we create JPEG files, right? That format is called raster format. Why this is used is we send satellites to Earth. These satellites using cameras scan the Earth and create these pictures. So the resultant pictures are basically the photos. So this format is called raster format. The another format is called vector format. A popular format is EPS, SVG formats. So this is the format for vector. So in the vector format, we do not take photos. Instead, we represent the information using three things: point, line, and polygon. For example, if I want to represent a highway, I represent it using lines. If I want to represent a place, let us say University of Aizu, I represent it as a point or polygon. So this is the representation of vector format. So this is how the raster data looks like. For example, if you take any photograph, for in that photograph, we will have the x-axis value, the y-axis value. Okay, so x coordinate, y coordinate, and then we have bands. For example, some of the bands are red, green, and blue. Okay, so when we take the photo, we take the photo in R band, blue band, and green band, right? RGB, red, green, and blue bands. So this information exists in it. Although we see a image, okay, internally it is basically a CSV file with X coordinate, Y coordinate, and the band values. In our camera, we only take photos for three bands, that is R, G, and B. However, the cameras in the satellite, they take photos at various band frequencies. Okay, please keep that in mind. Now, when we are talking about vector data, here if you observe, we have the concept called object, and for that we don't have x and y. Instead, we represent it as point, line, or polygon. And for this, we try to capture the information. So this is how the vector format looks like. Now let us see how we can create or how we can use SQL to create spatial objects. Okay. First, the Postgres database by default do not support spatial queries. In order for the Postgres to support spatial queries, you need to enable the extension called PostGIS. So once you create a database, you have to use this command, create extension PostGIS, to empower your database to use spatial queries. Otherwise, your database will not allow you to use spatial SQL queries. In the beginning of the exercises, when you are creating your database accounts, you can check in your Moodle, all of you have executed this command in your Postgres database. Now let us see the commands. Create table, geometrics, name char, location, point. We can define like this. Okay. But here, when you use the word point, please keep in mind a point, if you say, it becomes geometry. Now, okay. So it is not advised because many GIS softwares do not recognize this data structure. So if you want the GIS softwares to recognize it, you have to use geometry shape. So please use geometry. Okay, so create table, geometrics, name, and the location as geometry. You can specify like this. Okay, so this is geometry. Geometry means two-dimensional place. You have x-axis, you have y-axis, and you are putting the value. Geometry with geography means you are considering the earth, and this is the projection system. So you are saying create table, table name, that is geometrics. For this table, we have two attributes. One is the name and another one is geometry, which is storing the geographic information of the points using the projection system called 4326. So this is how we create tables for storing spatial data. Now, when you want to insert the data, then you have to use the following query. Insert into table name. So if you have many attributes, you can define those attributes. Then values. Put the values of the non-spatial attributes. Afterwards, you have to define like this. You have to define the projection type. What is the projection? That is 4326. And then you have to define the object. This is how we have to insert the data. We should not simply say point minus 110 30, because if you are inserting like this, the database will not understand which projection, with reference to which projection you are inserting this point. So we have to mention like this to insert the data. In today's exercise, you will be working on this data set. So please keep that in mind. Now, after inserting the data, if you use the query, say select the geom attribute from geometrics, when you print it, you cannot read the output because the geometric information is stored in non-human readable format. In particular, the geometric information or geography information of spatial objects is stored in hexadecimal system. So if you want to read the spatial information of the objects, you have to use this function. Select st as text and then specify the attribute from table. So if you execute like this, then the output can be read by the human. Next, like in any programming language, we have casting, right? So you want to convert an integer to string, a string into a integer, so on and so forth. In the spatial context also, we need this casting. For example, you have data in geometric format and you want to convert this geometric format into geography format. Okay, that is from two-dimensional plane to three-dimensional plane. To do this casting, we have this approach. So you can say select the point, cast it into geometry. Similarly, if we have the point information in geography, we are asking the system to convert it into geometry. That is, convert the 3D point into a 2D point. Next, this is the most important command that we often use. We often want to measure the spatial distances between the objects. To calculate the spatial distances between the objects, we have to use the inbuilt function called st underscore distance. So this is the function that you have to use to calculate the distance between the spatial objects. So I told you, if the spatial objects are geometric, then the st distance will return the minimum to the Cartesian distance, that is square root of x2 minus x1 whole square plus y2 minus y1 whole square. So that will be given. If the spatial objects have geography, then we use different method. For example, we think of it as a spheroid and we try to convert it. Okay, you don't need to do the coding, just use this function to get it. We have some examples by which you can understand. Assume we have this table. You can think of this table as create table, station info, station name, and the station location. Assume you have this table. Now you want to measure the distances between the various stations. To do so, we can execute like this. Select a dot name. What is a, we will see later. Okay. So we are saying select a dot name, that is station name, b dot name, another name of the station, comma, st distance. We are asking it to measure the distance from a geometry. Okay, so this is the spatial attribute and this is spatial be spatial attribute from geometrics here. So we are taking the table geometrics, we are doing the join of this table to itself by saying A, B, and then we are measuring the distance. Okay, in this case, I don't want to measure the distance to myself because it is already 0. So if you execute such a command, it will tell from Aizu to Fukushima, this is the distance. Similarly, from Aizu to Koriyama, this is the distance, and so on. Okay, so that's all for today's class. Thank you very much. If you have any doubts, please put message to me and I will try to answer it. Now open your test computers and answer the quiz. Thank you.